Hello, everyone, and welcome to today's webinar, Dose-fractionated EELS Spectrum Imaging Acquisition with Direct Detection Cameras. Before we get started, I'd like to cover a few housekeeping items. If you have a question, please submit it through the questions pane on your console. Any issues regarding connectivity and webinar viewing will be addressed immediately. We will attempt to answer any questions for the speaker at the end of the presentation. If we don't get to your question, we'll follow up later via email. Now I'd like to introduce the speaker for today's webinar. Dr. Liam Spillane has been working in the field of electron microscopy for the past 18 years. He started his career as a PhD student at Imperial College London studying oxide thin films using aberration-corrected STEM and monochromated EELS. After completing his PhD, he worked as a postdoctoral research assistant in advanced electron microscopy, working on the structural and chemical characterization of materials across a number of projects, including nanoparticle toxicology, ferroelectrics, nanoparticle catalysts, and solid oxide fuel cells. After leaving Imperial College in 2012, Dr. Spillane joined Gatan, initially working with the UK Sales and Service Group for a number of years. He relocated to Gatan, USA in Pleasanton, California in 2018, where he is currently the application scientist for Gatan's STEM, EELS, and GIF products. Now over to Liam.
Thanks, Jonathan. Great introduction. And thanks everyone for attending the webinar and signing up. So title is Dose-fractionated EELS Spectrum Image Acquisition with Direct Detection Cameras. So essentially, this is a kind of a walkthrough, talk-through of some of the exciting experiments and projects that we've been working on, either internally at Gatan or with kind of external partners. Probably most of the data is pretty new, so maybe a year or less old. Okay, so let's get started. So we're talking about direct detection cameras or counting cameras. So let's just have an overview of detector technology. So we have two types of counting detector. So the first you can see here on the left is what we call a counting monolithic direct detection camera. So this is like the K2 or the K3 or the Metro, Alpine, etc. type sensor. So we have an active detector where the electrons are directly measured at the sensor levels. That's why it's called a direct detector. The important thing here is this sensor is ultra thin, so it's a transmission sensor. The electrons essentially just go through that sensor. They don't stop, but we're just measuring them kind of as they pass by. Pixels here are very, very small, so just a few microns. So this is what we call a large format counting detector. So you have a large number of pixels in the array, so thousands, like 4K or 4+. So what's the second type of camera? Okay, so we have a thresholding hybrid pixel direct detection camera. So this is very, very different to the monolithic sensor. So the primary electron actually comes first into this silicon diode layer, where it essentially deposits all of its energy and generates electron hole pairs. So we have a thick silicon diode, so approximately 300 microns, generate electron hole pairs. And then that's bump bonded to an ASIC chip below for the readout. So essentially the charge kind of drifts through this bump bond into the ASIC chip where the readout then occurs. Now the pixels here are much, much bigger. So we're looking at like tens or multiple tens of microns. So the range for the pixel size here is 55 to 150 microns. The Stellar camera that Gatan have, for example, is 75 micron pixels. So much bigger than the monolithic system. Okay, so what you tend to have is fewer larger pixels in the same kind of approximate sensor or detector area, okay? But the commonality here is that they are both counting cameras. What's the benefit of the counting camera? So the whole point and the real great thing about these detectors is they kind of reject readout noise. So they're essentially very low noise or close to zero readout noise, okay? So that gives us some really kind of novel and different ways that you can run this hardware compared to a traditional like scintillator-based camera. And the thing that we're going to focus on today is what we call dose fractionation, okay? So dose fractionation really works well with these counting cameras because of this readout noise rejection. So what is dose fractionation? So it's actually something that kind of originated in cryo-EM, and it's a means of essentially, it's kind of like a motion correction technique. So the benefit of the counting camera, right, is that you can acquire lots of low contrast or noisy kind of subframes. But when you add those all together, because we just have Poisson noise, they'll add up to something that is quite good data at the end because we don't have readout noise. Okay, so you can basically run this systems very, very fast, do this motion correction or dose fractionation, and then kind of recover image resolution that would have basically been lost due to sample drift, sample motion. You also have the benefit of you get like a time series of data, which we'll see later, and then you have some flexibility about like kind of rejecting like damaged frames or something. So yeah, so this is very established in cryo-EM. Okay, so it's been around for like 10 plus years, and it's kind of a go-to method in cryo. So let's have a look at this one. Okay, so have this like simple video of kind of a low frame rate setup on the left versus a higher frame rate setup on the right. Okay, so 40 FPS versus 1500 FPS in this frame, and then essentially, the little cursor doesn't work, so let's stop the pointer, laser off. Okay, yeah, so there we go, that's what it's supposed to look like. So yeah, motion correction or dose fractionation in our like high frame rate K3 image on the right versus 40 FPS. And it's basically the resolution in these images kind of has a direct tangible outcome. So it kind of affects the resolution in these biomolecules, the resolutions for the reconstructions downstream in the processing pipeline. So as I said, this is not some sort of niche strange thing. This is a go-to technique in single particle reconstruction. And it's really led the resolution revolution, this kind of technology and this kind of dose fractionation method. So these direct detection counting cameras have really kind of made a paradigm shift in cryo-EM. And the number of structures that are solved kind of using these cameras and using this methodology just is growing with time. So this is kind of a nice little plot at the bottom here, just showing kind of the number of maps or structures that are solved and submitted to this online database, EMDB database. And you can see that with time, so 2020, 21, 22, 23, 24, that the number of structures is just kind of exploding in that number that are being solved with like these Gatan counting cameras. Okay, so cryo-EM kind of was the launch pad for the K2 and the K3, but I'm kind of more of a material scientist and physics background, so I'm kind of interested in what this means, or is this applicable for us in the material science world? And the answer is most definitely yes. Okay, so how does dose fractionation look in material science? Okay, so there's been a number of kind of works historically in this realm. The first of which, or kind of the seminal paper work, was done by Lewis Jones out of, I think, Oxford at the time, but he's now in Trinity College in Ireland, and kind of explored doing multi-pass spectrum imaging for kind of damage reduction or like resolution or signal to noise ratio, like enhancement. And if you kind of look at this figure that Lewis has top left here in his publication, we've got like a slow scan in the top left, the top row versus a 5 multi-pass scan in the bottom row. And it's very obvious that the fast multi-pass scan is superior to the single slow scan. So massive amount of damage in the single slow scan, no damage in the fast scan. And then there's kind of like resolution and features that can be seen in the multi-pass data that you don't see in the other data. So ADF, EELS, and EDS. Now, this was all done with CCD-based technology. how does that kind of stack up with the counting camera? So the counting cameras are going to give advantages, as I've already said, with respect to like kind of the noise performance of that detector. So there's been some kind of early work that was done by Robert Colby and Dave McComb at OSU. I think Bob was at Exxon, and did some kind of dose fractionation with a K2 multipass with like polymer samples. Now, this was actually done at a time that sort of predated our kind of in-situ software in digital micrograph and predated the K3. And yes, so now we have a new product, which we call in-situ spectrum imaging, which really kind of makes this a whole lot easier and kind of more capable, in addition to having kind of newer detection technology. So what is in-situ spectrum imaging? Okay, so essentially it is multiple pass spectrum imaging, which has been around for some time in the software, only we are now saving these passes individually as a time series. So it supports everything in SI, so EELS, EDS, 4D STEM, and kind of works like this. So you just essentially get pass 1, pass 2, pass 3. So we get our data cubes coming in sequentially, like kind of very, very rapidly. And that data is streamed to a high speed, high capacity RAID array. So typically multiple terabytes. So we're not constrained to the system memory. We just are constrained by this huge RAID array. So you can basically acquire data indefinitely with respect to that RAID capacity. So multiple terabytes is a lot more than hundreds of gigabytes of memory. We can do continuous scanning, continuous drift correction. So these two things become incredibly important when you scan very, very fast, okay? So if your spectrum images are only taking a couple of seconds to acquire, you don't want to be stopping and starting to do drift measurements, because that will add significant dead time, okay? You don't want to add 2 seconds to data that takes 2 seconds to acquire. It would be a bad strategy. But that is no longer the case. So continuous scanning, continuous drift. So this has been around for some time now. So we released this feature in 2023, October. So a couple of years nearly. Digital micrograph 3.6, and we've made some new improvements in 3.62, which is shortly to be released. One of the big ones is that this continuous scanning and drift correction can now be done with 4D STEM as well as EELS and EDS. So basically just as fast as EELS and EDS. That's an overview of the in-situ spectrum imaging kind of feature, and this is what we really use for dose fractionation, okay? And it's with the 2 counting cameras, and most of my data is EELS, so we're going to be in kind of EELS land from the rest of the presentation. So the EELS frame rates are as follows for the counting camera: 3,000 spectra per second for the K3, 9,000 spectra per second for the Stellar. So multiple thousands of spectra per second with continuous scanning and continuous drift correction. So that's what we're really leveraging to do this dose fractionation. So speed, okay? Speed is important. So we already saw that speed was important for the cryo work, okay? The slower we were going, the worse that motion correction is. And you're kind of going to have a similar behavior with STEM, right? STEM is a serial imaging technique, so speed is also important. If we want to go absolutely full speed with a STEM spectrum imaging experiment, we basically we have to get 1 readout per SI pixel. So we have to get at least 1 spectrum per pixel. Now that is going to define a few things, okay? So field of view. Faster readout is going to give us a larger field of view per unit time for a given pixel resolution. So a nice example of that is shown on the right-hand side here. So this is a dose fractionation time series that was acquired from the Stellar camera. Okay, so that large field of view is what we would get at 9,000 spectra per second. So we're getting 7 seconds per pass, atomic resolution. I think the pixel size there is 1/4 of an angstrom. So you get like a decent amount of field of view, right? 9,000 spectra per second. Now, if you look at that little cutout at the right, so what I've shown there is from essentially a cutout from the same area, and that's the equivalent size of the field of view that we would get with a K2 running at 400 FPS. So much, 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 much smaller if we want the same pixel resolution at the same magnification. And that's just purely the frame rate difference in the camera. Okay, so field of view. Dose rate. So faster readout means that we're going to get shorter probe dwell time per sample position. Kind of sounds obvious, but that's going to reduce the electron dose rate significantly. So we can basically work at larger field of views per unit time for the same resolution, and we can go faster. So we have access to higher or lower dose rates. Now, just something that I've been working on a lot recently, atomic resolution spectroscopy. And my kind of go-to numbers for this now are pretty short, okay? So I'm targeting, sorry, not pixel times. I'm targeting a scan time, like so the whole pass there, less than 10 seconds. And that's for kind of easy standard samples. So if you can get each spectrum image pass in less than 10 seconds, this works every time. If the samples are more challenging, so high drift rate, or if you just put it in the microscope and want to image immediately, then probably something less than 5 seconds is going to work better. So the faster you go, the less rigid or like non-rigid artifacts you're going to have in each scan, and the less the drift is. So the drift correction just works really, really well. So speed is important, and essentially these counting cameras allow us to go at these crazy high speeds, which is fantastic. So that's kind of an overview of the technology, the history, and now we're going to walk through the kind of application examples that I want to focus on. So the first of which is CryoSTEM. So CryoSTEM. So this is something that has been demonstrated before, actually. So really nice work by Barrett when she was at Cornell, 2020. I think the experiments actually started a few years before that, but this was published in Archive on 2020. So Barrett was able to do atomic resolution EELS mapping using the K2. Because that's a super sensitive camera, this was possible just a probe current of 85 picoamps with a single EELS readout of 2.5 milliseconds for those SI pixels. So this is a single pass, no drift correction. So really, really nice atomic EELS and STEM there that Barrett kind of published in this paper. Now, this is highly challenging at cryogenic temperatures due to stage drift. So the question is, like, how does current generation counting camera technology with dose fractionation compare? So we can now go like much, much faster, and we can do dose fractionation. So this is a very challenging, like, so this was done in 35 seconds at Cornell per scan, but this is quite a long time compared to like what we've been doing in the last few months. So to have the sample stay kind of stable for 35 seconds in a cryo holder, like the hit rate on having this like succeed with a 35-second capture time is going to be kind of low. So it's going to be very, very difficult. Okay, so let's move on to the newer data. So what am I looking at here? Strontium ruthenate, dysprosium scandate. Okay, so this is a great test system. It's beam sensitive oxide on a very radiation hard sample substrate. So that's kind of cool. We can look at something that's beam sensitive, and we can look at something that's essentially indestructible in the same experiment. And it's a really nice, beautiful epitaxial thin film. So we can look at interface chemistry, atomic resolution spectroscopy, and so forth. So this sample was very kindly kind of given to us or lent to us by Barrett again. Barrett's now at Max Planck Institute for Chemical Physics in Dresden. And I've actually done this at room temperature, and the sample was so beam sensitive that I then decided to run this in a cryo holder. So this was done in the office at Pleasanton on our Joel F200, so no CS corrector, very low probe current of 20 picoamps with a double tilt cooling holder. I got data from K3 and Stellar, but the majority of the data I'm showing here is K3 data. So if you kind of look at the little video that's been looping on the left, if anyone hasn't figured it out already, this was me recording this experiment live when I was quite excited to see it working on the microscope. So that's the live experiment. We can clearly see atomic resolution in the single ADF frames, and that's the temperature of the cryo holder. So let's take a look at the data. Okay, so first slide, we have just the single pass. So K3 2D array, and the raw data, the raw frames were 360 by 50 pixels, okay? 339 microseconds per pixel. So we can do that large array in just over 6 seconds. And 420 passes, continuous drift correction enabled. Now, the ADF has some kind of workable resolution here. We can basically see atomic resolution. SNR is not great, but the maps, the EELS data at this point don't look all that compelling. So we can kind of get a hint that the scandium is where it's supposed to be, but everything else doesn't tell us a whole lot. If we zoom in, it's the same. We zoom into the noisy kind of unclean data and just shows us more of the same. Where things get interesting here is when we do the summation. So we have the time series. So the first thing that is done is a post-acquisition drift refinement. I can also then discard non-rigid frames. So doing these two things left me with 234 passes. The one thing to kind of just point out before I go any further is look at how many passes I've discarded, right? And I'm going like really quick here, like 6 seconds per frame, and I still had to discard a large number of the frames. So the faster that you go, the less non-rigid artifacts you can get in each of these frames. So our stellar pass times when I'm doing this are more like 3 seconds instead of 6 seconds. And the 3-second data is much easier to drift correct than the 6-second data. Okay, so 234 passes and data looks fantastic. So we get high SNR atomic resolution in everything here, right? So the ADF image and all of our maps, even up to ruthenium L at 2800 eV. So this is just raw summed aerial density. Like, there is no denoising, no filtering in this data whatsoever. You can see really great, you can kind of see the distortion in the unit cell of dysprosium scandate in the ADF. You can see the ruthenium, strontium structure, really fantastic interface resolution here in the ADF. And this is, remember, this is uncorrected, and this is with a 20 picoamp probe current. And then we've got atomic resolution in the scandium, the dysprosium, the strontium, and the ruthenium maps. What do the spectra look like? Okay, so we've got all the ionization edges, major and minor, in our target energy range. So ruthenium M45, scandium L23, ruthenium M3, and so on, all the way out to our like ruthenium L23. So 3110 energy range. So this is a single spectral range. We're not doing any kind of multi-range here. And we're getting 0.9 eV effective energy resolution because of the sharp point spread function of the detector. So we're able to do this massive energy range with decent energy resolution. And this would be very kind of adequate for us to do like LNES analysis on the oxygen K or any of the other ionization edges in the sample. What else do we have? So if we kind of look more at the atomic resolution maps, we see periodic contrast, proximal spacing 4 angstrom in all the data without denoising, and everything's where it's supposed to be. So the ADF intensity maxima and minima are in good agreement with the cation positions in all the maps, and for the two structures in the substrate and the thin film. So this is like a summation of all of the data. So one of the things that's important, particularly when we're doing something with dose fractionation, is that we don't necessarily know when this is going to damage, okay? So what we tend to do is we acquire very low dose per frame but medium or high total dose. So what you're seeing now at the bottom is actually the accumulating data in that time series. And that's useful because that allows us to think or figure out like how many of these frames do I need to get like atomic resolution in my scandium or atomic resolution in my ruthenium. And obviously those numbers are going to be different. We're going to get high spatial resolution or kind of high SNR and the low energy loss signals first, right? But yeah, in the context of damage, we don't necessarily want to sum the whole thing, right? Because maybe it's damaged by past 20 or maybe it's damaged by past 30. So our maps here look fantastic when we sum the whole series, but kind of the trick is that we want to sum like the minimum number required to get the result that we need. So this ability to do this dose tuning for different outcomes is a real kind of strong and powerful thing with this dose fractionation series. So we can do this after acquisition, and to get the highest spatial resolution, we can essentially sum more time slices and we can sum less spatial pixels. But with the exact same data set, if we said, actually, I'm really interested in dose and I want the lowest dose. So we could, instead of doing lots of time summation, we can sum less time and we can sum more spatial pixels. So we could say spatial resolution is less important for this measurement than this measurement. And we can do the same thing with the one data set. So yeah, with this data set in particular, I started to notice that patches form in the SRO layer. That kind of is indicative of electron beam damage. This is something that is, the analysis here is far from complete, and this is just the first kind of round. So I think we also need to do some oxygen K, ELNES analysis, and ELNES analysis on those ruthenium edges, and see if there's any changes in chemistry, and try to determine which is our kind of cutoff pass that we want to work under. I think just in the first round, it seems like we probably shouldn't go higher than past 30. And that is an accumulated pixel time of 10 milliseconds. So just for like fun and interest, I was kind of like, okay, so how does that compare to a traditional CCD-like acquisition, like if we were to do 10 milliseconds? So just as a recap, with the spectrum imaging with counting cameras, we basically always go as fast as possible and then do this post-acquisition like summation. Okay, so with the K3, 339 microseconds and run it full speed. If we were to do a CCD-like acquisition, what we want to do is maximize the signal per read. We want to minimize the number of reads and minimize the read noise. So, okay, if we look at the same numbers, we'd say we're not going to run at 339 microseconds. We are going to run a single acquisition at 10 milliseconds. Now, how does that stack up compared to this dose fractionation series that we've just seen? So the slow readout is very, very different, okay? So this is actually different data. So this is stellar data on the left, 9,000 spectra per second. So 110 microsecond pixel times versus 10 milliseconds on the right. So many, many, many scans are happening on the left before we've even completed a single pass on the right. So the left-hand data was continuous drift correction, multi-pass, and this is like row-based drift correction on the right. So slow, we've kind of given up and finished with the one on the left, okay? So massive differences. So the data on the left was like less than 4 seconds per pass. The one on the right is multiple minutes per pass. So you can kind of see the degradation in the slow scan, which is not unexpected. So significant discontinuities due to the row-based drift correction instead of the continuous multipass. The interface is kind of like sheared and warped. So essentially, we have a catastrophic loss in resolution by going slow. So this experiment just will fail if you run this slowly. And this is going to be true of many experiments. Like the speed makes it incredibly easy. If those pixels are kind of in the kind of microsecond realm, this kind of acquisition becomes like routine. If you're doing like milliseconds or higher, the chance of success like drops kind of quite drastically. Okay, so that's a lot of time I've spent talking about the strontium ruthenate dysprosium scandate. So a material science cryo-EM example, and ending on this like super high speed versus kind of slow single pass acquisition. So let's stay in the realm of cryo, and we're going to switch gears and look at a bio-cryo example, so biology. So a nice kind of starter for this is to think about doses. So electron doses in STEM spectrum imaging. So the typical electron dose for high resolution STEM EELS experiments with a sub-angstrom probe are super high. So if anyone hasn't kind of done this calculation, you'll probably be shocked. So by HR STEM, I mean atomic resolution. So example doses for a subatomic probe, so 0.8 angstroms with a 0.25 angstrom SI pixel size. So these are fairly typical numbers for HR STEM. So 200 picoamps versus 20 picoamps, and we're looking at like 10 millisecond pixel time versus 110 microsecond pixel time. So let's start on the high side. So 10 millisecond dwell time with a 200 picoamp probe gives 2 times 10 to the 8 electrons per angstrom squared. If we 10x reduce the current down to 20 picoamps, then the dose comes down. And then, so this is a very, very low current of something that we would do in material science typically. And then if we use this low current with the fastest camera that we have, so 110 microseconds, the dose has come down like significantly, right? Three orders of magnitude. So 2 times 10 to the 5 electrons instead of 2 times 10 to the 8. Now, if we kind of compare that with a cryo-EM dose, we're not even in the same room. So the maximum total dose for imaging in cryo-EM is typically 40 electrons per angstrom squared. So this is like still 4 orders of magnitude lower than what we're typically going to have with a low probe current STEM experiment. So this doesn't really sound hopeful, right? If we want to do EELS mapping in like a biomaterial, sounds like we're done. However, that is not the case. So dose fractionation and direct detection, excuse me, actually allow us to achieve what might have seemed impossible from the previous slide. So we can actually do elemental analysis of materials in bio like samples. So this is like a frozen cell section, mitochondrial granules in human retinal cells. So this is some work that was done in collaboration with Hua Chu's group out of Stanford and was recently published in bioRxiv at the moment, December 2024. So kind of really exciting work. So being able to do STEM spectrum imaging, EELS mapping in like kind of cryo-EM conditions. So how is it that we can do this? So there's a few things that are important. So these dose rates can be achieved if the following strategy is followed. So there's a few things that are important. So ultra low probe current, for example, 3.7 picoamps. I'm giving you the exact numbers that we use on our microscope. So very low current. And then the important thing is a defocused probe. So the features that we're targeting here are not like atomic resolution. So defocusing the probe significantly reduces the electron dose. So a nanometer probe instead of an angstrom probe. Direct detection counting. So we have next to no signal with this setup. So we did this with the K3 camera. This is really critical, okay? So ultra low current, very weak signals anyway, use a counting camera. And then the final thing is to make the spectrum image pixels large and leverage the hardware synchronized sub-scanning capability of the Digiscan 3. So 8H sub-scan with an 8 nanometer pixel size, 1 nanometer probe, right? So these 3 or 4 things combined gave us super low dose. So we were able to achieve a dose rate per spectrum image, or kind of dose per spectrum image, of just 18 electrons per angstrom squared. So significantly less than we had on the previous slide. And this is something that is palatable for a biology experiment. So the data. So the first thing that we did is identify a region of the sample. That was actually done with TEM, and then do a preliminary dose series to see when the thing gets damaged. So what you're looking at on the right is the dose fractionation series. This is the ADF data, and we're interested in when those holes form in the sample. And we want to make sure that we get our data before that degradation occurs in our time series. So with this data, 15 passes, right? So 15 passes is what we get. And that's an accumulated dose of 300 or just over 300 electrons per angstrom squared. And then we just run multiple different ROIs, acquire lots of things with those probe currents, those pixel sizes, and so forth. So yeah, do the dose fractionation series, do some post drift refinement, some collapse, just keep the good frames. We obviously don't keep the full 15 and keep all the holes, and then do our EELS mapping from the summed and cropped data. Okay, so we've got the carbon map, nitrogen, oxygen, calcium, and then a nice RGB composite. So the scientific question in this particular project is actually, where is the calcium? What's the distribution of the calcium? So the question is like, is calcium in these kind of little mitochondrial granules in the sample? So after the mapping, what happened next? We can actually then go and look at the spectra to verify this data. So we can selectively sum in these bright regions. Yep, so that's basically what all of the red is here. And then some in just the cellular matrix. So essentially avoid the bright regions. And then we can compare like a spectral fingerprint in these kind of granules versus the non-granule area. And if we kind of look down in the bottom left, it's very clear that the calcium, or the detectable calcium, is, localized to these granules. So calcium L edge is strong in the red spectrum, and the intensity is low or absent in the blue spectrum. We've probably got enough resolution here to do LNES analysis, but that wasn't really the project. Okay, so that's the cryo example. So we have one more example, which is going to go in a completely different direction. So instead of low dose, we're going to move to something that is much like higher dose, where the signal is very, very, very low. So ultra high energy loss. So this example is something that my colleague Andrew Throne worked on a lot, I think, last year. And it's a really, really nice example of what can be done in space of high energy loss EELS with counting cameras. So detecting weak core loss signals. So Andrew's gone and done elemental mapping and LNES analysis of cobalt, iron, and manganese K edges. So not L edges, he's looking at K edges. So the energy loss range that he targeted is 6,000 to 8,000 EV. So super high energy loss. Now this sample is just like a mixed iron cobalt oxide. So it's not beam sensitive, but these signals are ultra weak. So very, very low scattering in these transition metal K cross sections. So just to give you the context of that statement, this experiment was done with a 1.9 nanoamp probe, so incredibly high probe current, and still the total acquisition time was over an hour, so 1 hour and 10 minutes. So the dose, if we were to calculate the dose here, the zeros probably wouldn't fit on the screen if we compared it to the previous cryo-EM example. But for a non-beam sensitive sample, that is like less of an issue. Okay, so super long exposure time. How does like dose fractionation stack into this example? Well, if the experiment takes 1 hour and 10 minutes to acquire the data, dose fractionation is still super useful for us. So this example is using the Stellar. So the data is 2D array, 100 by 100, and 2.5 nanometer pixels. And yeah, we're still running the camera fast because that's how we run a counting camera. 500 microsecond pixels, and that gives us 5 seconds per pass. So this fast acquisition strategy is still good when we're requiring for an hour, because we can do high frequency drift correction and spread the dose, right? So even though we're spending 70 minutes acquiring the data, we're drift correcting every 5 seconds. So we're going to have good kind of spatial resolution in our maps or our data at the end. If we didn't do that, unlikely the sample would sit still for 70 minutes, potentially. Spread the dose. We don't want to leave the beam parked for goodness knows how long. The sample, even if it's radiation hard, okay? So parking the beam for very, very long periods of time is usually not the best strategy. Okay. So one kind of like final thing with this particular data set here is the manganese was not detectable if the full ROI here is sunned. So that's kind of important. So the manganese here is kind of localized to these kind of precipitates in the iron cobalt matrix. So just to show you what that looks like, the red kind of dash box here corresponds to the summation area in the spectrum image for the red spectrum here, and the blue spectrum corresponds to this stub ROI over in the manganese map, which is kind of localized to these particles. And if you look at the particle and if you look at the spectra here, difference is obvious. Jump ratio for the blue spectrum in the manganese K edge is good, and basically the jump ratio for the red spectrum is absent. So it's in this particular example, and it's probably true of many examples, it wouldn't be sufficient for us to just defocus the probe or work with a massive probe and have no spatial selectivity. We would not detect the thing that we're looking for, okay? Or we'd miss important information. So having like decent spatial resolution as well as like high sensitivity is, both of these things are important, okay? So yeah, really nice example that Andrew's done. So the final thing that he did with this data, he's even gone and done outness analysis of the cobalt K using non-linear least squares fitting. So the data quality that Andrew got with the hybrid pixel was enough to do peak analysis of this peak at 7,700 EV. Okay, so this is really quite fantastic, and you can leverage this with counting cameras. Okay, so yeah, really nice. Okay, so that's kind of drawing to the kind of end of the time that I wanted to spend on the data. So I'll move on to our summary slide. So 3 kind of main points that I wanted to get across here. So direct detection electron counting with dose fractionation has really revolutionized data acquisition and processing pipelines in single particle reconstruction in cryo-EM. So it's been massively adopted in the community. And I think we can expect to see the same benefits in materials science. Okay, so if we kind of do the same thing for our spectrum imaging experiments, we see huge benefits. So we kind of should be doing this. The dose-fractionated EELS SI essentially will make existing workflows more simple and routine. So I found that atomic resolution EELS mapping becomes super easy and essentially works every time if the spectrum image pass time is 10 seconds and I'm doing dose fractionation with Stellar or K3, right? So less than 10 seconds is sort of a magic number. And this experiment that I traditionally thought was really difficult works every time on our microscope and on any external microscope that I've done the same work. It's pretty, the hit rate is incredibly high. Okay, what else? Okay, so dose fractionated EELS spectrum imaging also gives us the potential to do completely new things. So we can do elemental mapping and analysis in cryo. So cryo-EM, that's something that we would have thought perhaps we could never do. Mapping in frozen cell sections, this allows us to do that. And then anything where we have really weak signals. So ultra high energy loss was the kind of the final example, but I'm sure everybody can think of other examples or other experiments where these techniques are really going to help. So that's kind of the final points that I wanted to say, and just wanted to thank everybody for attending and listening in. So that's probably a good break point for questions if there are any questions.
Hey, excellent presentation, Liam. Thank you so much. Hey, yeah, we did have a few questions come in, and a couple of them were related to the Cryo-bio experiment you were showing. You showed spectra that were just from the calcium-rich areas, and the question is how did you define those areas, and was that like automated segmentation, or is that kind of, how was that done?
Okay, that's a good question. So there's kind of two ways that can be done. So in this specific example, this is just a UI-based feature in the software. So you just have the spectrum image open in the software, and you can draw like a free path and make a closed loop around a feature. So in this case, it's this little, these little particles. We can basically draw whatever we want, and you can draw like kind of multiple closed loops at the same time. So in this case, 1, 2, 3, 4, 5, 6, 7. And with those kind of ROIs defined, then you just go to, I think, the SI menu in the software, and then there's a feature that says sum in selected region. And that's the simplest way to do that. You could do this programmatically if you wanted to write a script. So you could do the same thing where essentially use a Python script or a DM script to analyze the image and automatically find like particles or regions, and then programmatically do the summation as well. So there's kind of like two ways of doing it. We did the manual approach in this example because it was just kind of like there were not many data sets to work with, and it was faster time to result to do it by hand. But an automation pipeline, you might want to do a scripted version of the same thing.
And the same person asked, what was the black dot in the middle of the data?
Oh, the black dot, this one?
Yeah.
This was when we were not so familiar with the sensitivity of frozen cell sections, and that's actually a damage position. So we weren't very rigorous with where we were parking the beam, and made a small hole in the sample. So yeah, you need to be very careful, very careful.
Question about drift correction. So spatial drift correction is shown a lot here, but what about energy drift correction? Can you use that and get sharper EELS data?
So yes, so you can do drift correction spatially. You can also do energy correction. So there's two ways to do the energy correction. You can do it live. So ZLP lock is a great feature for removing energy drift on the fly. And then there's the kind of the post-acquisition approach. So in the SI menu, there's a function called align SI by peak, and that essentially does the same thing or similar post-acquisition. And both of those things are equally valid. I think I tend to use align SI by peak with these time series because I have the full stack, and that's just personal preference. But if you're not kind of doing dose fractionation and you're doing an accumulating sum, which is a feature in the software, then ZLP lock is then more appropriate because you don't have the time domain in the data like in the summation. But both both are kind of getting you the same result there with energy correction.
Great, great. And then another question about the Stella and the K3. So if you have both on your microscope, when would you choose one over the other?
That's a really good question. So this one, and yeah, this is a good. So this is the kind of a good test case for this as well. So like this one, so this stellar example where we were running at 9,000 spectra per second. This data was like much easier to process because it's 3 times faster. So usually if I'm like, I want to go as absolutely fast as possible, and I'm only mapping and I don't care about energy resolution, my go-to would be probably the Stellar, purely on speed, because it's easier to work with the data. Now, if I want to do an ELNES type analysis, then I kind of want my spectrum to look like this one, right? So this is an ideal scenario. I've got every ionization edge that I'm interested in the sample, and I have 0.9 EV energy resolution. So I can, with this K3 data set here, I can do fine structural analysis on the oxygen K, which in this experiment, this is important information to get out, right? We want to do ELNES analysis on the oxygen K. We probably want to do ELNES analysis on the ruthenium L, or at least have the option to. Now, these guys are quite far apart. So if we want to do this, the K3 is the absolute go-to, right? If we tried to do this with the Stellar, I don't have the data, but I can tell you that the energy resolution is going to be much worse at 200 kV. So it's going to be something like 6 EV, 9 EV. So we wouldn't be able to do the ELNES work. If we went to a spectral magnification where we could, so source resolution on the hybrid pixel, like Stellar, we need to work at a dispersion of 100 millieV per channel. So really that only buys us one of these edges at a time, which would be limiting. So yeah, usually I'd say like K3 if you're interested in actual like spectral analysis, or Stellar if you're just interested in mapping. But there is kind of overlap, and the kind of the key thing is to think about like what's the result that you need, what's the important thing, or what's limiting in the experiment. It's like, is 3,000 spectra fast enough? If it is, then 3,000 spectra, right? You've got like loads of benefits. But if you need to go at 9,000 spectra, then you kind of have to use the other camera. But definitely having both is wonderful, because you can do both experiments. Yeah, it's a really good question.
Yeah, I also might want to add that with the Stella, the point spread function gets better as you go to lower KVs. So when you're working at 60 or 80, 60, 30 kV, point spread function gets really, really good. Whereas the point spread function on K3 is a single pixel at 200, 300, and so there's a KV component there too. Actually, another question just came in. Maybe make this the last question. And I don't know the answer to this question. Do you need to have IS capability on the Stella camera to do dose fractionation spectrum imaging? And I believe all Stella cameras come with IS capability built in, but I don't know about spectrum image in-situ capability.
Yeah, I can't recall if that's an add-on or not.
So I'll have to get back to you on that one. But yeah, this presentation does leverage the IS capability of the imaging filters, and in-situ is not just for in-situ; it's also for dose fractionation, which turns out, equally as important.
Yeah, I would just say, yeah, I almost never don't do this now with any data. So this is not this kind of dose fractionation for EELS. We now acquire as routine, like the flexibility of being able to discard like bad frames, do this drift refinement at the end. It's very, very kind of compelling. It makes these kind of experiments night and day, like different. Like definitely. I'm surprised. Yeah, I don't know. Maybe not surprised anymore because I've done it so many times. But it is like this would have been like a hero, even kind of not in a cryo, right? Doing atomic resolution spectroscopy, particularly on a non-CS corrected system, is a real kind of long shot experiment. But we now, with this dose fractionation and the counting technology, these you can just acquire one, acquire another one, acquire another one, and acquire another one, and it becomes a routine workflow where this this just works every time. And I think it's yeah, the high speed, being able to add data without paying the noise price, and the high speed, just basically the drift rate is low enough with respect to the scan time that the algorithm can correct these kind of like subatomic shifts before you basically don't get unit cell hopping if you set it up nicely. And then in the data afterwards, you maybe have you might have 1 or 2 frames that are like where it made a mistake depending on the filtering, but you can correct that with this post acquisition refinement, and you end up with something that is really great data that would, I would say, otherwise be very, very hard to acquire. Yeah, so if you kind of want to do these kind of experiments, this is, in my opinion, the way, much easier way to do it than you might have experienced in the past.
Go-to way.
Yeah.
All right. Well, that's great. We're coming up on the top of the hour. And trying to answer a quick question here. Actually, why don't I'll just answer it for everybody. The question was about the dose fractionation in the cryo. What the experiment did is acquire the data first, saw that the damage had happened, and then went back into the data series and only kept the good frames. So that way you can just, even if you don't know what the damage threshold is, you can throw out the damage stuff after the fact.
Yeah.
That set the damage threshold, and then you don't have to know ahead of time.
Yeah, that's super useful to be able to do that.
All right. Okay. Well, thanks so much, Liam, and thanks everybody for joining in on a busy morning, afternoon, or depending on where you're coming in from, and enjoy the rest of your day.
Fantastic. Yeah, thanks everyone. And oh yeah, we have another webinar that's going to be in early June. So we'll be kind of starting to promote that next week. So if anyone's interested, like keep an eye on your inboxes, and it would be great to see everybody in the kind of the June webinar, kind of a continuation of this webinar series. So yeah, that's I guess everything that I had. And thanks again, and hopefully see you all in the next webinar.